of a substance goes up if I can increase the number of charge carriers. If we have dry air and it is cold, then the resistivity of cold, dry air at 1 atmosphere, so rho for air, cold, dry, 1 atmosphere. Cold means temperature that we have outside. It's about 4 times 10 to the 13. That is the resistivity of air. It is about what it is in this room, maybe a little lower because the temperature is a little higher. If I heat it up, the air, then the conductivity will go up. Resistivity will go down, because now I create oxygen and nitrogen ions by heating up the air. Remember when we had this lightning, the step leader came down, and we created a channel full of ions and electrons. It had a very low resistivity, a very high conductivity. And so what I want to demonstrate to you, that when I create ions in this room, that I can actually make the conductivity of air go up tremendously. Not only will the electrons move, but also the ions now will start to move. And the way I'm going to do that is I'm going to put charge on the electroscope. Oh, that is not so good. No harm done. I'm going to put charge on the electroscope, and you will see that the conductivity of air is so poor that it will stay there for hours. And then what I will do, I will create ions in the vicinity of the electroscope. Now let's first put some charge on the electroscope. I have here a glass rod, and I'll put some charge on it. Okay, that's a lot of charge. And the air is quite dry. Conductivity is very, very small. And so the charge cannot go off through the air to the surroundings, to the earth. But now I'm going to create ions there by heating it up. And I decided to do that with a candle, because a candle is very romantic, as we all know. So here I have this candle. Look how well the charge is holding, eh? And here's my candle. And I will bring the candle, maybe 20 centimeters from the electroscope. Look at it, look at it. It's already going. It's about 15 centimeters away. I'll take my candle away, and it stops again. So it's all due to the fact that I'm ionizing the air there, creating free electrons as well as ions, and they both participate now in the current, and the charge can flow away from the electroscope to the earth because the conductivity now is so much higher. I stop again, and it stops. You see in front of your eyes how important the temperature is, in this case, the presence of the ions in the air. If I have clean distilled water, I mean clean water. I don't mean the stuff that you get in Cambridge. Let alone that I mean the stuff that is in the Charles River. I mean clean water that has a pH of 7. That means 1 out of 10 to the 7 of the water molecules is ionized, H plus and OH minus. The conductivity, by the way, is not the result of the free electrons, but is really the result of these H plus and OH minus ions. It's one of the cases whereby not the electrons are a major responsibility for the current. if I add 3% of salt in terms of weight, then all that salt will ionize, so you get sodium plus and Cl minus ions. You increase the number of ions by an enormous factor. And so the conductivity will soar up by a factor of 300,000 or up to 1,000,000, because you increase the ions by that amount. And so it's no surprise then for you that the conductivity of seawater is 1,000,000 times higher. Think about it, 1,000,000 times higher than the conductivity of distilled water. And I would like to give you the number for water. So this is distilled water. That is about 2 times 10 to the 5th ohm meters. That is the resistivity. 2 times 10 to the 5 ohm meters. I have here a bucket of distilled water. I'll make a drawing for you on the blackboard there. So here is a bucket of distilled water. And in there is a copper plate, another copper plate, and here is a light bulb. And this will go straight to the outlet. Stick it in, 110 volts. This light bulb has 800 ohm resistance when it is hot. You see the light bulb here. You can calculate what this resistance is between the 2 plates. That's easy. You have all the tools now. If you know the distance, it's about 20 centimeters. And you know the surface area of the plates, because remember, the resistance is inversely proportional with A. So you have to take that into account. And you take the resistivity of water into account. It's a trivial calculation. You can calculate what the resistance is of this portion here. And I found that this resistance here is about 2 mega ohms. 2 million ohms. So when I plug this into the wall, the current that will flow is extremely low because it has to go through the 800 ohms and through the 2 mega ohms. So you won't see anything. The light bulb will not show any light. But now, if I put salt in here, if I